Okay, so in this problem, we are going to try to figure out the work needed to bring a 6 microcoulomb charge from infinity, and we'll just say infinity is down here, just draw a little ellipse here, right? So take it from infinitely far away to right here. Now, it doesn't matter what route we take. We can take it from infinity and go woo here, okay? Because these forces are conservative forces. It's just like gravity as well, okay? So I'm going to take this charge, a 6 microcoulomb charge, and I'm going to put it here. Now the way you do these step by step is you want to find the initial voltage, find the final voltage. The change in voltage is final minus initial, okay? Just you got to remember that, right? That's always like, let's say you're growing, right? Your change in height is the height at the end of the year minus the height at the beginning of the year. That's how you would get a positive number, right? And then the final thing is that we're going to use the formula. The potential energy is change in voltage times charge. And that comes from the definition of voltage, which is that it's the potential energy divided by the charge, right? If you solve that for the work, it's voltage, change in voltage times charge, right? Okay? So for this one, the initial voltage is at infinity, right? And the formula is that it's K Q over R, and so K Q over infinity is how you say it's 0. Okay, so infinitely far away from charges, the voltage is always 0. Okay, so now let's find the final voltage. That's the fun one. That's the voltage right here. That's our final, right? This is our initial. Well, the final voltage is going to be the voltage due to both of these charges, right? So that's going to be 8.99 E9, and the formula I'm using here is V is KQ over R, right? Okay, times 1.5 E minus 6, and then this, if it's 24 centimeters from side to side, then this must be 0.12 meters, and this must be 0.12 meters. All right, so divided by 0.12, and then of course we add the same thing, right? 8.99 E9. This guy is E minus 6 divided by 0.12. Now, we could just say 2 times that, but I'm not gonna, because I know what the next PowerPoint slide says. Okay, so 8.99 E9 times 1.5 E minus 6 divided by 0.12 plus 8.99 E9 times 0.5 E minus 6 divided by 0.12. Okay, so when I do this, I get, let me make sure I've got it right. I get that the voltage is 224,750. All right, that's our V final. V initial is 0, so final minus initial. So subtract 0, right? Our delta V is exactly this, right? 224,750, right? That's our delta V. Okay, and now I'm all set. I can simply go, work is change in voltage times charge, right? So 224,750 joules of work for every coulomb times 6.00 E minus 6 coulombs. So times 6 E minus 6, and I get, that's 1.3485 joules, which with 3 sig figs we'd have to say 1.35 joules. Okay? Now, so that's example 1. That's pretty simple. Whenever they say from infinity, infinity just means voltage equals 0. Okay, so you don't have to actually calculate that one to some place, right? So you do these 4 steps: initial voltage, final, find the change, and then multiply the change by the charge. Let me do another one for you. Now it's here, it's right at that position right there, which, by the way, don't we know that this voltage right here, I'm taking this charge out of the way, right? Okay. Well, we know the potential there, if we take this guy out of there, is 224,750 volts, right? And then we're going to move it to 8 centimeters closer to this charge, right? Okay, well, we need to know what this voltage is here, right? Okay, so what we do is when we calculate this, we calculate it without the 6 microcoulomb charge there. We find the voltage that's there, and then we multiply, okay? So I'll just show you what you do here. So let's find this voltage. This voltage is going to be equal to 8.99 E9 times 1.5 E minus 6 divided by 0.08 for this one. All right, that's the left charge, right? And then we're going to do this guy, right? So 8.99 E9 times 1.5 E minus 6 over 0.16. And this is going to be for the right one. It's hard to say because they're both the same charge. They're both positive, right? Okay, so now, hey, look at that. I have this all typed into my calculator. So all I have to do is make that 0.08. 8.99. Okay, and then I'm going to make this. Okay, 0.16. I'm typing this in one swell foop. And this voltage is 252,843.75. So this is our initial voltage. This is our final voltage, right? The change in voltage is final minus initial, is V final minus V initial. So that's 250,843.75. That's a 4. Minus 224,750. It's going to be a positive change, right? So that minus 224. And I get that it's positive 28,093.75. Okay, that's our voltage, right? Okay. And then our last step is that the work is change in voltage times charge. And in this case, this charge here is the moved charge. Right? Charge, moved charged. And that's our 6 microcoulombs, right? Okay, so I'm going to do the change in voltage. It's 28,000. Right, times, and this is joules per coulomb of change in voltage, right? Times the moved charge, which is 6.00 E minus 6 coulombs. So times 6 E minus 6, and I get 0.16856 joules of work. Five 1685625. Now, if this had, these have only 2 sig figs, so I guess we'd have to say 0.17 joules. If we'd made this like 6.0, right, then we'd have a couple sig figs, yeah? Okay, so step 1, find the initial voltage. Step 2, find the final voltage. Step 3, final minus initial is change. Step 4, multiply the change by the moved charge, right? So up until now, we've ignored the moved charge. We didn't use it in this calculation. We didn't use it to calculate that on the previous slide, right? We only use it, we use it only at the end here. We got the change in voltage from this position to this position times that charge. Yay? Yeah, these are like some of the hardest ones.